Okay, everybody, we will go ahead and get started. I'm sorry to have to do this again. I anticipate being back on Friday. Couple of questions coming in about the exam. I think your syllabus or whatever or Learning Suite says the test closes at 9 p.m. tomorrow. But the testing center is open till 10 p.m. That's not intended to be a trick. That just didn't pay attention to when the testing center closes. So yes, you'll have until the testing center closes to finish your exam. Will the test cover nomenclature? Not in any particular detail. I think the practice exam maybe threw some of you for a loop, especially the one about the aldehydes. But in general, no, it shouldn't be a major deal on the nomenclature shouldn't be a major deal on the exam. All right. Anything else? All right. Well, we're going to begin today on Chapter 17. And Chapter 17 and 18 are all about chemistry of carbonyls, but this time at the alpha carbon. And so far, everything we've been doing has focused on the carbonyl carbon. So we're going to talk about what you can do at the alpha carbon, going to introduce some new reactions, but it's still nucleophile attacks electrophile, HOMO attacks LUMO. And I understand that many of you are not yet ready to move on to new material. You're worrying about this exam that's currently open, and that's fine. We'll go ahead and just try to make space in your mind to just follow along today, and then as you have time in the future, you can go back and review the notes and get started on the Chapter 17 study guide, which is currently posted on Learning Suite. Okay, so what do we mean by alpha carbon? Here's your typical ketone, carbonyl carbon, alpha carbon. We're using the term alpha to describe a carbon or a position that is one bond away from a functional group of interest. So this carbon is alpha to the carbonyl carbon. But it turns out that, and you may already anticipate this, the proton that's alpha to this ketone has a pKa that's much lower than your run-of-the-mill sp3 hybridized carbon-hydrogen bond. So if you go back to Chapter 2 or a pKa table and look it up, you could see that the pKa of the proton on this just regular sp3 hybridized carbon is around 50. Whereas the pKa of the proton alpha to a carbonyl is substantially lower by 10 to the 30 orders of magnitude. All right, there's some trouble hearing the audio. Okay. Sorry about that. It looks like audio is coming through for a lot of people, so check your headphones if audio is a problem. So that's 10 to the 30 or 30 orders of magnitude, which is just an astronomical number. And so to consider the reasons why, we of course draw the conjugate base. I guess I'll fill in the other protons that are implied but not previously shown. This conjugate base is a primary carbanion. This conjugate base with a negative charge at the alpha carbon is resonance stabilized because of the presence of the carbon-oxygen pi bond adjacent to the alpha carbon. In other words, I can draw a resonance structure where I move the electrons that used to be on the alpha carbon and put them in this pi bond. And then I take the electrons that, used to be in this pi bond and I put them out on this oxygen. So resonance delocalization, as you know from 351, spreading out of a negative charge through space via resonance is favorable and makes the conjugate base more stable than just a localized negative charge. So I think some of you probably had some experience with pi systems and conjugation in 351. If you did, what I'm about to say may make sense. If you didn't, it might not make sense, and don't necessarily worry about it. But structurally, what you have in this conjugate base, which we're going to call an enolate, is you have three atoms that are each sp2 hybridized, and they're in a conjugated system. And we can imagine that we get this conjugated system by mixing a p orbital on the oxygen with a p orbital on carbon with a p orbital on the alpha carbon. And what that would look like, is something like this, right? A p orbital on oxygen, a p orbital on carbon, and a p orbital on the alpha carbon. And in the world of MO theory, you can mix three orbitals together to get three new pi molecular orbitals. And the lowest energy one has each of those p orbitals together side by side in phase, or rather with the same wave function sign. There's a node in the plane of the page here. This is the first pi molecular orbital. The second pi molecular orbital looks like this. It has a lobe on the oxygen and the alpha carbon, but not on the carbonyl carbon. Oops, that's not what I meant to do. Here, color just represents wave function sign. When the wave function sign switches, as it does when going from this lobe to this lobe, that means that you go through zero and there's a node in the middle. That node happens to coincide with the position of the carbonyl carbon. And then the highest energy orbital would be the one where the three p orbitals are adjacent to each other, but with opposite wave function sign. This is what the three pi molecular orbitals look like. In the case of the enolate, we have 4 electrons involved in resonance, the purple ones and the red ones. And so we fill the 2 bottom orbitals. This lowest energy orbital represents the electrons that are spending time in between oxygen, carbon, and carbonyl carbon and the alpha carbon, and sort of represent this pi bond that's delocalized across all 3 atoms. The highest energy electrons, notice, are only in this orbital. They're only on the oxygen and on the alpha carbon, and that corresponds to the lone pair with the negative charge that is only ever on the alpha carbon and on the oxygen. So that's just a crash course reminder in resonance, but resonance is the explanation for why the enolate is more acidic than a typical sp3 hybridized carbon-hydrogen bond. Now, we've dealt with a lot of different carbonyl compounds. And their pKa's, the pKa of the alpha carbon of these various carbonyl compounds varies in a way that is pretty straightforward to rationalize. So I'm going to start with the least acidic alpha protons. We don't need to memorize pKa's, but the trends will be useful. So the first, let's see. Our first carbonyl compound is going to be the amide. And we'll be considering the acidity of this alpha proton. The pKa is 30, so notice relative to the ketone I showed you earlier, that's about 10 billion times less acidic. Okay. Then if you go to the ester, that pKa of that alpha proton is 25. And then we can continue to the ketone, where we've said the pKa is 20. And then the aldehyde, where the pKa is 17. Okay? So notice the trend. We go from least acidic alpha proton to most acidic alpha protons. And notice that the trend tracks with how electron rich the carbonyl carbon is. So to explain this, let's consider resonance for an amide. We can draw a resonance structure for an amide in which we take lone pair electrons on the nitrogen and make a new pi bond between nitrogen and carbonyl carbon. That would put a positive formal charge on the nitrogen and a negative formal charge on the oxygen. So the nitrogen is acting as an electron donor, and the if the nitrogen donates electron density via this resonance structure, the carbonyl carbon is less electron poor. What should that have to do with acidity of that alpha proton? Well, consider the reason that alpha protons are acidic in the first place, and that is they can delocalize their electrons. The conjugate base can delocalize its electrons into the carbonyl. So you would predict that more electron poor carbonyls should have more acidic alpha protons, because if the carbonyl is electron poor, that's going to make it even more favorable for this negative charge to delocalize into the carbonyl. So the fact that the amide nitrogen is already donating into the carbonyl makes it, and I'm going to draw the conjugate base here, makes it less favorable to have a negative charge on that alpha carbon. Again, because in addition to the resonance structure where the enolate, where the negative charge on the alpha carbon is delocalized onto the carbonyl oxygen like we saw up here, when you've got that nitrogen acting as an electron donating group, you have this resonance structure that puts those two negative charges close together. All right, I'm not sure I've explained that well. That seemed kind of convoluted to me. The basic idea is that if your carbonyl carbon is electron poor, it will be more favorable to make the enolate because the resulting negative charge is going to be better stabilized. Any questions you want to ask about that? Anything you want to say to clarify? Yeah. That's right. Yeah. Enolate acidity of the carbonyl compound is based on these two resonance structures where the negative charge on the alpha carbon can be delocalized onto the carbonyl oxygen. But that's going to be less favorable if you're already donating electron density into that carbonyl carbon. Other questions? Okay, so with that in mind, then why is the ester 100,000 times more acidic than the amide? And the reason has to do with, again, the viability of an alternative resonance structure. So you can draw a resonance structure where lone pairs on the ester oxygen donate into the carbonyl and put a negative charge on the oxygen. Doing that makes the alpha proton less acidic, and to see why, again, we can think of these three resonance structures and consider how good each of them are. Oops. So the ester has the same problem as the amide does, in that the ester oxygen can donate electron density into the carbonyl carbon. The reason that the ester is more acidic is because oxygen is not as good an electron donor as nitrogen due to oxygen electronegativity. Okay, from that perspective, this also tracks with carbonyl reactivity, right? If we were to make another column here for how reactive these carbonyl groups are, aldehydes are more reactive than ketones. Esters are more reactive than amides. Okay. What about the difference between the ester and the ketone? Why do we see it getting even more acidic? Well, in the ketone, the group you've got on the other side of the carbonyl is just a methyl group. It cannot donate electron density via resonance. It is a weak electron donor via what's called an inductive effect. And this has to do with the fact that the carbonyl carbon is sp2 hybridized and is more electronegative than an sp3 hybridized carbon. So sp3 hybridized carbons donate electron density into the carbonyl carbon via just a dipole kind of effect. And so the more alkyl groups you have, the less electron poor the carbonyl is going to be. But this donating effect due to electronegativity is not as powerful as is the resonance effect for the oxygen. So despite the weak donating effect of the alkyl group isn't able to well, let's just say it this way. The oxygen on the ester, because of its resonance donation, makes the ester carbonyl carbon less electron poor than in the ketone, because the methyl group in the ketone or the other alkyl group in the ketone is not as good an electron donor as is the oxygen. And then this same idea explains why the aldehyde is much more acidic than the ketone, and that is because the aldehyde has fewer sp3 hybridized carbons on the carbonyl carbon. So that means less inductive electron donation. Okay, so the trend is that the more electron poor your carbonyl is, the more acidic the alpha proton is going to be. Okay, any questions? All right. There are some other even more acidic alpha carbons. You can imagine that the thing that made an alpha carbon acidic in the first place was this neighboring carbonyl group. And you could ask the question, what if we had two neighboring carbonyl groups? So let's draw the following diester. Often we're going to use abbreviations for small alkyl groups. An ethyl group is just, ET stands for an ethyl group. ME stands for a methyl group, and so on. The alpha carbon here, proton has a pKa of 13. Now compare that to the pKa of a regular ester, which is 25. That's 12 orders of magnitude, or about 1 trillion times more acidic. And that's because you now have two, if you draw the conjugate base, you now have two carbonyls into which you can move the negative charge on the alpha carbon. So you've got this resonance structure, you have this one, and then you have this one. Okay, can you see how because this carbon, the alpha carbon, is actually alpha to two carbonyl carbons, we can donate electrons this way, or we can delocalize those electrons on the alpha carbon in that direction. Or we can delocalize them in the other direction with the other carbonyl. And just it's a minor nomenclature issue, but it's going to come up again and again in terms of how we talk about these compounds. Molecules like this that have an alpha carbon that's alpha to two carbonyls, we sometimes call these beta dicarbonyl compounds, because it doesn't matter which carbonyl you start counting from, the other carbonyl is at the beta position relative to the other carbonyl. So this would be a beta diester. And notice this pKa of 13. That starts to be acidic enough that, that the alpha proton of this beta diester can be completely removed by like hydroxide or some alkoxide. And we've thought of these, I think, before as relatively strong bases, but it turns out that we're going to need, for the carbonyl compounds we've talked about previously with pKa's of this sort of nature, we're going to need a base that's quite a bit stronger than hydroxide or an alkoxide if we want to get complete enolate deprotonation. So this just gives you a sense for how acidic it is when you have the two carbonyls beta to each other. And so we can continue, and the trend sort of follows. If we replace one of those two esters with a ketone, and remember, ketone carbonyls are not as electron poor as ketone carbonyls are more electron poor than ester carbonyls. Ketone carbonyls are even more electron poor than ester carbonyls, so you would predict that this alpha proton that's alpha to an ester and a ketone should be more acidic than the beta diester, and indeed that's the case, though it's only by about 100-fold. We'll call this compound a beta keto ester, because it's got a ketone that's beta to the ester. And then you can mix and match various carbonyl compounds, but if you go to the beta diketone, the alpha proton has a pKa of 9, which means that proton is very, very easy to remove. Okay, so this is just a sense for the acidity of alpha protons. Are there questions you want to ask? And if you have a question while I'm talking, feel free to type it in the chat. I'm monitoring the chat and I can answer questions that way as well. Yeah, that's right. And again, I'm not going to waste your time on exam saying, is this a beta whatever? Which of the following is a beta keto ester? That would be kind of a lame question to ask. But as we talk in lecture, I'm going to use these terms. And later on, I want you to pay attention to beta dicarbonyl compounds, because later on we're going to see that as a pattern for something interesting that can happen. In particular, we're going to see these two molecules again in the end of chapter 17. We're going to use them for interesting chemistry, and they're going to have a unique step at the very end that's going to be attributable to the fact that there's a carbonyl on the beta carbon. So it's useful to recognize that pattern. All right. Others? Okay, with this in mind, we've talked a lot about these enolates. I want to just mention that the first few sections of chapter 17 have to do with the fact that you can undergo tautomerization to get an enol instead of a ketone. And presumably the way this happens is first some base removes a proton from the alpha carbon to get you the enolate, and then next the enolate gets protonated on the negatively charged oxygen, and that gives you the enol. So this is tautomerization, and you may have done it before without realizing what you were doing or why the alpha proton was particularly acidic. This is the keto form. This is the enol form. And in general, the keto form is usually more stable. And that is because carbon-oxygen bonds are more stable than carbon-carbon bonds. So it's better to have a carbon-oxygen pi bond than it is to have a carbon-carbon pi bond. Your text takes you through some examples where the enol form is unusually stable. I don't know that we need to talk a lot about that. Here's an example. The enol of the beta diketone we just dealt with here is very stable because you've got conjugation and an intramolecular hydrogen bond. And some people would even argue that what I'm about to draw is not an equilibrium structure, but is instead a resonance structure. Instead a resonance structure of the other compound. In other words, some people think that this is an equilibrium where this proton belongs to this oxygen and then gets traded to the other one. Other people believe that these two are actually resonance structures of each other, in which case each oxygen shares the proton evenly. So just be able to recognize the acidity of alpha carbons, alpha to ketones, and then being able to get from the keto form to the enol form is important, and recognizing situations where enols are more stable is useful too. Okay. So we're now going to talk about two different ways of forming enolates. And the reason for this is not going to be apparent at the beginning, but it will become clear a little bit later on. So the first method of enolate formation is reversible or equilibrating enolate formation. What do we mean by that? Well, imagine you take our ketone that we started with, and imagine you use as a base let's just use OH minus, okay? Now the pKa of this alpha proton we've said is 20. And if we imagine what the position of this equilibrium is, we could draw the conjugate base. By the way, it's always okay to draw the enolate in either of the two resonance structures. I'm going to typically draw it this way because a lot of the chemistry we're going to do is going to be at the alpha carbon, but there's nothing wrong with drawing the enolate this way. And whether you see either resonance structure, you need to be aware of the idea that the negative charge is on both the alpha carbon and on the oxygen. So the conjugate base of the ketone is the enolate. The conjugate acid of OH minus is water. So, and of course the pKa of a proton on water is around 16. So if you compare the pKa's, and this is a chapter 2 problem from 351, which side wins? The most acidic acid loses its proton. And so we would say that actually this equilibrium favors starting materials way more than products. And it's by 4 orders of magnitude. So that means at equilibrium, 99.99, I think that's about right. 99.99% of your starting materials are still starting materials, with only about less than 0.01% enolate. Okay? What that means is that all the time we expose this ketone to this base, we form enolate and then it goes back to starting materials, and we form enolate and it goes back to starting materials, and the rate of going back to starting materials is so much faster than the rate of going to the enolate that we have mostly this with only a small amount of this. Why would you want to do this in the first place? Why would you want to do this in the first place? Well, it turns out that even 0.01% enolate is enough to do some chemistry with. And by Le Chatelier's principle, if I shunt off this enolate into some other product, that's going to pull the equilibrium forward, generate more enolate, which can then go and react to make product. So despite the fact that there's not very much present, that you can do chemistry that way. And the great thing about hydroxide or alkoxides is that they are cheap, they're readily available, and they are not moisture sensitive, so you don't have to use special conditions to use those reagents. Great question on the chat. If organometallic compounds are strong bases with pKa similar to sp3 hybridized carbon, why don't they remove alpha protons instead of attacking the carbonyl carbon? That is an excellent question. I like that one a lot. So let's just imagine this aldehyde. What about an organolithium? You were told that organolithiums attack at the carbonyl carbon to give you a tetrahedral intermediate. And now you're saying, hold on, why not attack at the alpha carbon? I agree that attacking at the alpha carbon seems like a perfectly reasonable thing to do. I don't recall when we first introduced organolithium reagents, I said you could think of them like carbanions, but the reality is somewhat more complicated. So I think many of these organolithium reagents tend to aggregate, and so you end up with weird structures like this. And I'm not making this stuff up. There's actually strong evidence for this kind of thing in even larger aggregates. And my guess is that that kind of structure, though it's okay for attacking the carbonyl oxygen, maybe makes the carbon less basic. That's hand wavy. So I'm sorry for that explanation, but you're right to think about it as an issue. And I think the answer is, first, well, even if we don't know why, it actually works. So, but then I think if you want a reason, I think somehow the partially covalent bond with the lithium must make this a little bit less basic. But I agree. It's a good question. It's a difficult issue. In general, we're not going to use organometallic reagents to remove protons on alpha carbons. Okay. Oops. All right, so why does it matter? What would be the consequences of using reversible or equilibrating enolate formation? It doesn't look like there's much of anything to worry about for this particular ketone, but what if we started with a different ketone? What if we started with this one, where you have an alpha proton here and an alpha proton there, and those two alpha protons are not equivalent, All right. And let's imagine what would happen if you used hydroxide as a base there. Again, you're going to expect, sort of more than 99.99% starting materials. But let's consider the equilibria. Let's consider whether at equilibrium one enolate is going to be favored over another. So let's draw both enolates. In purple, I'm going to draw the enolate you get when you remove the purple alpha proton. And I'm also going to draw its resonance structure for a reason you'll see in just a minute. Then let's draw orange alpha proton, or the orange enolate, the one we get from removing the orange alpha proton, and I will also draw its resonance structure Okay. So we have this situation where two possibilities are in competition with each other. And now is why we care about the fact that this is reversible or equilibrating. Because if both enolates are in equilibrium with the same starting material, that means that the enolates are also in equilibrium with each other. Which means anytime two things are in equilibrium with each other, the one that is the major, the one that is formed in greater amounts is the one that's more stable. So under reversible enolate formation, the most stable enolate is the dominant enolate. So what would we say here? Which of the two enolates is more stable? Turns out enolate stability is going to track with alkene stability. So more substituted enolates are going to be more stable. We're talking about the substitution of this pi bond. More substituted enolates are more stable, whereas less substituted enolates are less stable. So what we're saying is maybe at equilibrium we have something like 0.01% of the more stable enolate, and then way, way, way less than something way, way, way less than 0.1% of the less substituted enolate. In other words, these are equilibrating conditions. In either case, we still have the majority of our starting material is still in the ketone form. And because every time OH picks off a proton, it goes to the enolate and then comes back, on average, whatever enolate we have, we're going to have more, on average, whatever small amount of enolate is present, more of that small amount is going to be the more substituted enolate than the less substituted enolate. Again, that's kind of tricky, a bit convoluted. I'm not sure I've explained it well. So what questions do you want to ask? What is the goal of this reaction when there is such low yield? Well, we're going to see that you can use enolates even in such small amounts as nucleophiles in a subsequent step. So suppose you took this ketone and you exposed it to a strong base, and then you made a small amount of enolate, and then you said, let's add an alkyl halide. At that point, the enolate can act as a nucleophile with the alpha carbon attacking the electrophile in sort of an SN2 fashion. And that's going to break the carbon-bromine bond, and that's going to make a new carbon-carbon bond with the alpha carbon. Now notice that if we reacted that, that the product would be different from the orange enolate, right? If this is the enolate that we form, the product we get is going to be this one. So there's an issue of regioselectivity here. But let me back up. Why did we do this in the first place? It turns out that even the very small amount of enolate that forms is enough to start the reaction with this alkyl halide. And then as the reaction progresses, as more enolate reacts with alkyl halide and goes to product, then more starting material will go to enolate. Austin, you're asking, when you add OH minus to the reaction, why does it also attack the ketone carbon in a nucleophilic addition reaction? Yes, that would be another side equilibrium that's going on. In general, that kind of thing, like hydrate formation, is happening in solution. And the issue is that this doesn't go anywhere. So even though that's a side equilibrium, the fact that we're using an alkyl halide electrophile draws us towards these products. Another side equilibrium for each of these would be Enol formation. Right, and the enolates in all of these cases are high energy intermediates, but what I'm saying is there's just more of the purple one than there is of the orange one. So when they go to react, we're going to get more of the purple product than the orange product. How does the stability of the enolate affect the basicity of the oxygen? So I presume you're asking about the oxygen on the enolate oxygen. And that's a good question. I think I'm going to answer it this way. You'll notice in the enolate, the alpha carbon and the carbonyl oxygen are both share the negative charge, and so are both electron rich. Nevertheless, for the most part, enolates are going to be nucleophilic on the alpha carbon rather than on the oxygen. This has to do with oxygen's electronegativity and with a molecular orbital argument that's a bit beyond what I want to talk about in this class. I guess, I suppose if you want to know, the short answer is the most reactive electrons in the molecule are these electrons that are shared between carbonyl, oxygen, and alpha carbon. And if you do the molecular orbital calculations, the amount of this orbital on the oxygen is smaller than on the carbon. So the HOMO reacts on the carbon because that's where most of the HOMO is. This lowest energy orbital is similarly biased toward the oxygen side. That's a result of MO theory calculations. It's sort of beyond the scope of the class. If you want to just memorize that in general, enolates are going to be reactive at the alpha carbon, that's fine, and that's useful. And that's why I'm going to choose to draw the enolate resonance structure this way. Okay. Yeah. That's a good question. Is it more reactive in terms of nucleophilicity? Yeah, I think we can answer that question best with an energy diagram. What you're essentially asking about is kinetics and versus thermodynamics. So the short answer to that is that the more stable enolate is going to be the one that through which the reaction goes. But I will try to answer that next time a little bit better with an energy diagram that'll hopefully make things a little clearer. Yeah. All right, that's about all we have time for today, folks. I will see you in person on Friday.